We've talked about how, in bond-forming reactions, areas of positive charge like to interact with areas of negative charge. And we've seen how to identify Lewis acids and bases in reactions. Chemists like to be specific in showing what the electrons are doing in this type of reaction. So we'll spend some time diagramming Lewis acid-base reactions. To diagram a reaction, we need to start out by drawing Lewis structures of the reactants and products. In doing so, we should be able to identify what bonds form during the reaction and what bonds, if any, break during a reaction. For the new bonds that form, we can identify the Lewis base and the Lewis acid. Recall that the base is the source of the electrons for the new bond, and the acid is the acceptor of the electrons. What's new here is using curved arrows to show where the electrons go when new bonds are formed, or old bonds are broken. For the new bonds, the arrows start at the base, literally at the electrons that are shared, and end at the specific atom that accepts the electrons. Our first example is this reaction, where silver reacts with two ammonias to form a new complex ion. For our purposes here, the product is simply a polyatomic ion. We start by drawing the reactants and the products. We identify the new bonds that form, in this case, two new silver-nitrogen bonds. Hopefully we can see that the electrons that start out as lone pairs on nitrogen end up as the shared pairs in the product. So the nitrogens provide the electrons for the new bonds, and we can identify the ammonia molecules as the Lewis bases. It shouldn't be a surprise that, with its positive charge, silver ion is the Lewis acid. The final part of diagramming the reaction is adding the curved arrows to show where the electrons go. Since the electrons go from the nitrogen toward the silver, so do the arrows, one from the left and one from the right. In our next example, carbon dioxide reacts with hydroxide to form the hydrogen carbonate ion. We again start with the Lewis structures of the reactants and products. We can see that the new bond that forms is the carbon-oxygen bond to the right. Notice that in the reactant, that oxygen on hydroxide has 3 lone pairs and 1 single bond. In the product, it has 2 lone pairs and 2 single bonds. One of its lone pairs has been converted into a shared pair. That allows us to assign the hydroxide as the Lewis base and the carbon dioxide as the Lewis acid. Carbon dioxide as an acid is understandable, since the oxygen on the hydroxide, being electron-rich, would be looking for the electron-poor atom on CO2. And based on electronegativity, carbon should be partial positive. So to diagram the reaction, we need to add the curved arrow to show electrons from oxygen being shared with the carbon. But notice that is not the only change from reactant to product. We also see that the double bond to the bottom oxygen has changed to a single bond. This happens in order to maintain the octetic carbon. Carbon has 8 electrons around it in both the reactant and the product. In order to maintain octets, bonds are formed and broken simultaneously. We need to add a second arrow to show that the bond breaking, or in this case converting from a double bond to a single bond. Again, the arrow starts at the electrons, since we're showing where they're going, and points to an atom. In our final example, sulfur trioxide reacts with water to form sulfuric acid. This reaction is in large part responsible for what we called acid rain, where products of sulfur combustion combine with water in the atmosphere to result in a strong acid. There are actually multiple pathways this could occur, but we state here that the first step is SO bond formation, and we want to diagram the first step. So we draw the Lewis structures. Notice when we line the molecules up like this in the reactants, we can see how the partial positive sulfur in SO3 is lined up across from the partial negative oxygen in water. So a new SO bond makes sense. You could also reasonably propose that the partial positive hydrogen on water bonds with the partial negative oxygen on SO3. But we've stated in the problem that the SO bond forms first, so that's what we've drawn in the product. On going from reactant to product, we notice two changes. The new SO bond forms, but the old SO double bond on SO3 converts to a single bond. Again, we form a bond and break a bond to maintain the octet at sulfur. We should be able to see that the lone pair that starts on water oxygen, highlighted in red, ends up as a shared pair in the product, while a shared pair in the double bond in the reactant, highlighted in blue, ends up as a lone pair in the product. To diagram the reaction, we need to add two curved arrows, which both start at electrons and point toward atoms. First for the bond that forms, then for the bond that breaks. In this reaction, as we've diagrammed it, SO3 is the acid and water is the base. By the way, the product shown here is actually not the final product. The two hydrogens on sulfuric acid are on different oxygen atoms, so there would be subsequent steps to get the hydrogens aligned properly. But we have diagrammed the first step.